Madeline, Nicholas,
Hello.
greetings this fine evening. I came in early, Nicholas, because Madeline sent me a email about some stuff she was screwing up, and so we said, let's meet early.
Yep. If you have any questions about double angle identities, I am sure to learn from them because I'm having a rough time with them.
Yeah. Do you have a question formulated, or would you like me to ramble? Actually, I mean, pick one of the assignment questions that gave you trouble. Tell me what it is, and let's talk about it. You're on mute, Madeline.
Question 2 was where I got a lot of problems. For whatever reason, question 1 I got right like the first time I tried it. And then question 2 I was working on for like an hour and I just could not figure it out. So if we want to go over specifically cosine, double angle identities, I guess that would be the best place to start, because I guess based on the first question, I don't really have problems with sine double angle identities.
Okay. So let's see, we are told that, at least in my problem, the cosine of x equals 3/5. And the tangent is less than 0. So I have the same problem in my calculus class. We're having this exact discussion today just because it's the conceptual understanding of this takes some time. But when you see the cosine of x is 3/5, you should immediately say, oh, x is an angle. Because I'm taking the cosine of it, it's an angle. That's what you take the cosine of, is angles. And then, of course, there's a fraction on the other side because cosine is adjacent over hypotenuse. So, hey, that's a right triangle with an angle x. And the two of the sides are 3/5. And so you should see that as code for right triangle, angle x. Cosine is adjacent over hypotenuse. So that means this side would be 3 and this side would be 5. Are you cool with that, Madeline?
Yes, so far I've been able to, draw out my little reference triangle and everything. It mainly just comes to when I am using the equations on my little sheet. I assume it's like an algebra problem. I have no idea what I'm doing wrong.
Yeah. So since we got this drawn, let's keep going. I know this side would also be 4 then, thanks to Pythagorean theorem, which is nice. It was nice of them to make up a problem with a 3 and a 5 in it. So that other side was a whole number, square root of 16. But then I'm told the tangent is negative. So if the tangent is negative, the tangent of x is 4/3. That's not negative, that's positive. So how do I fix that?
It's located in the fourth quadrant where y is negative.
Yeah, cosine is x coordinate.
X is not.
And so this same exact triangle could exist in the fourth quadrant where this is angle x, this is the adjacent, and this is the hypotenuse. Notice 3 is still positive because I'm going right 3, but I'm going down 4. So if I put that in the fourth quadrant, cosine.
And that would make tangent of x equals negative 4/3.
Exactly, in which case, ching, we met that requirement. Tangent of x is negative. So that was just kind of a tricky way. It would have been nice if they just told us, hey, put this in the fourth quadrant. But instead they thought, oh, let's just be tricky. But if tangent is negative, fine. I'm in the fourth quadrant. It's the same triangle. It's just now we have a negative sign for 4. While we're here, let's just write some other stuff down just because we can. Like, don't even, The best way to do math is not to try to answer the question, but just to stop and think. Like for instance, I could also say that the sine of x being opposite over hypotenuse, that'd be 4 fifths. We already know the cosine of x. The tangent of x, we already discussed. I actually don't need to rewrite it. It's right there. Tangent of x would be 4/3. And so, cool. And I could go on and list cotangent and secant and cosecant. I could list all of them if I wanted to. But that's just kind of cool to say, okay, great. I got all those things. Now, if we're asked for whatever, say the sine of 2x, well, that's double the angle, so I can't do it. This was your question, Cole. So I can't find double the angle, but an identity that I can look up that we looked at last time says, hey, sine of 2x is equal to is the same thing as 2 times the sine of x times the cosine of x. That's really cool because I can't do this because I don't know what the angle is and I don't know what double it is, but I do know this version. So didn't we just decide above that the sine of x was really negative 4/5, and weren't we given the fact that the cosine of x was 3/5? So this is just saying 2 times negative 4/5 times 3/5. If I multiply that out, what do I get? Negative 24 over 25, I think. Notice I never even figured out what the angle is. I don't even know what the angle is. I can figure it out if I want to by going inverse cosine and find that angle if I want. That's kind of cool. What if I'm asked for the cosine of 2x? Well, there's identities for that. I happen to have memorized the sine of 2x. I don't have memorized those, so let's go. I'm going to go get it. So let's see. What options do I have for the cosine of 2x? Oh, that's right. That was that one that had all kinds of options. Interestingly, this one, if I choose this one right here, does it make sense I could have answered this from the start without drawing any of those pictures? Because
Yes.
you know, that recipe only requires cosine, and I already knew that it was 3/5. But we know sine now too, so I could actually pick any of those three since I know what the sine of x is. But let's pick the one we know. So 2 cosine squared. And notice this time they just named the angle theta instead of x, but it's the same formula. So, wow, I'm dumb. I went away for 2 seconds and I already can't remember it. 2 cosine squared minus 1. Except I'll rewrite it with an x. So that's 2 times, well, cosine is 3/5. Cosine of the angle is 3/5. It's still squared minus 1. So 3/5 squared is 9/25. 2 times that is 18/25 minus 25/25. All right, so I have a common denominator. I guess that'd be negative 7/25. I think that's the answer if I haven't blown it. You got to think of this as recipes. Recipes, ingredients. I don't even like to cook. I'm being asked for something, I don't even know what it is. And I don't know because it's got double the angle, and I don't know what double the angle is. But it's equal to, that's what identity just means, identical. It's identical to this. And that recipe calls for something I do have. I don't have any 2x's in my closet, but I do have cosine of x. I have that. Hey, I can make that. What do you think, Madeline and Cole?
It makes a bit more sense. I think where I was getting caught up was the negatives,
Mm-hmm.
was realizing that like, oh, in order to make tangent less than 0 or greater than 0 or whatever the problem wants, I have to put it in this quadrant, which means that this number is negative and
Wow,
all sorts of stuff.
that's right. None of which is obvious, but this is very algebraic. In other words, there's reasons for things, and I've got to draw pictures and slow down and make sense of it and so forth. Now here's a cool little cheat. The tangent of an angle isn't tangent. One of the identities for tangent is, isn't it equal to the sine of whatever angle you happen to be talking about divided by the cosine?
Yes.
Don't I already know those two? Like there's the sine of 2 theta, there's the cosine. So couldn't I just use that if I wanted to? Yes. Could you also use the identity for tangent, which I have no idea what it is? There it is. I could do that too. Either one of those, I'm going to get the same exact answer.
If you do the sine 2x over cosine 2x, would you not get a positive number for tangent 2x?
Yeah, you would. So sine over cosine, that'd be negative 24/25 divided by 7/25, which is times the reciprocal. Hey, look, those cancel, and you'd get 24/7. Just for the fun of it, even though it won't be fun.
Yeah, but isn't that not allowed for what the question is saying? Because if tangent has to be less than 0.
Yeah, but remember, it's tangent of 2 theta. In other words, whatever this angle is, you're twice as big. So we don't even really know what angle we're at. We're doubling that angle. So given that I'm sitting here in the 4th quadrant, that angle might be something like 300 degrees. And if I double that, I'm at 600 degrees. So it's like, I got to think about where that is, but I'm not in the 4th quadrant anymore if I double that angle.
Okay.
That's a good question. So let's just check our work while you're thinking on that. So the tangent is equal to 2 tangent, 1 minus tangent squared. So that's equal to 2 tangent, 1 minus tangent squared. And again, I really like this one instead because it's asking for the tangent of the angle, not tangent of double the angle. I don't know what double the angle is, but I do know what tangent is. We figured it out that it was negative 4/3 earlier. And again, you would have messed that up, Malin, because you were talking about screwing up the negative and so forth. So if the tangent of x is negative 4/3, then that'd be 2 times negative 4/3 on the top. And negative 4/3 squared, of course, the squared means it doesn't care whether it's positive or negative because it's going to make it positive when I square it, right? So I get negative 8/3 since you multiply fractions straight across. And you get 1 minus 16/9, 4/3 times 4/3. And let's see, that'd be negative 8/3 divided by 16/9. I'm sorry, 9/9 minus 16/9 would be negative 7/9, I think. In other words, that's 9/9. Let's see, negative 7/9. So it's a negative divided by a negative, which is a positive. So I end up with negative 8/3 times the reciprocal 9/7 negative. This 3 and that 9 cancel. Hey, look, negative 8 times negative 3, positive 24 divided by 7 times 1. Hey, I got the same exact answer. That's really cool. Of course I did. So you want to look at this as just purely algebra. Like you got so many formulas now that you kind of don't you can't even keep them all in your head anymore. They're just there and they're floating around, and I got to look them up on a sheet and so forth. But anytime I see something, anytime I see the cosine of 2x or the tangent of 2x, I should think, hey, there's some other way to write that. If I want to, I can write it some other way. I wonder what that way is. I got to look it up. And then just let algebra do its work.
Basically, any action that doesn't require the attack or special inputs in any way can still be done.
Say that one more time. What do you think?
It makes a bit more sense now that we've gone over it kind of again before we started class. And also having looked back at my homework and thinking like the correct answer versus the answers that I kept getting, I think it makes more sense now.
Yeah. It takes practice because it actually depends on everything you've done in this class so far. I mean, the whole unit circle thing is something I usually find that people either didn't study enough on, the teacher didn't teach it clearly enough. It takes more practice. Maybe after you try it, maybe a second explanation, but you want to really own the unit circle so that you can draw these things out. You want to deeply understand SOHCAHTOA because all of this is based on SOHCAHTOA. So you can draw a triangle. Anytime you see trig, you should think, oh, right triangle. I think I'll draw one and kind of see what the heck, this is talking about, because it doesn't make any sense to me. Angel, you sent me a question too in the chat or in the messages, which I managed not to notice until like 30 minutes ago. I'd like to start out just kind of addressing some of those just so people feel good about it.
Yeah, let's see. In the homework, it was question 4 and 5. So I kind of reworked some of the answer, the questions, and I'm still coming up with, missing one of the 3 or 4 answers. Like I'm not, not sure why that is.
Yeah, so let's answer, just because I think it'd be good for everybody. I want to pull up your question again. And write it down.
Like in question 4, one of the answers was -1/2. And I don't know where the negative came from.
Yeah, I had problems on questions 3 and 4 as well.
Yeah, those are the equation solving ones. So let me just pull up what I get for question 3 and I'll write it down. So this will be really similar to what you got. They even used a Greek letter. So 2 times some angle. Remember, if you're taking the sine of it or the cosine of it, it's an angle. But what I don't like, the first thing I see about this that I'm really not happy with is the fact that I'm happy that they're both sine because I can solve an equation, but it has just one trig equation in it. And remember, you're always trying to get it to a place where it's like the cosine of the angle equals some number, because then I can go inverse cosine to solve it. But I have to get it down to one trig expression. So I'm happy there's a sine, but then I look a little closer and I realize, this one is one angle and that one's another. They're like not even the same size. So they're two different angles. Frustrating. But then I think, wait, the sine of 2 times an angle, that was one of those identities, identicals. There's another way to write that. And the sine of 2 times an angle is the same as 2 times the sine of just the angle, not double the angle, times the cosine of just the angle, minus 8 sine of the angle equals 0. So I'm happy now because I only have one angle. I don't have two different angles. I'm unhappy because now I got two trig equations. I got a sine and a cosine. So not cool. Like this is very, very much of a mess. But here's where basic algebra skills kick in. In other words, hey, look, there's a minus sign here. Distributive law says, look, this one's got a sign and this one's got a sign. So does it make sense I could pull that out of both of them? And then what does that leave behind? 2 times 6, it leaves 12 times the cosine of the angle minus 8. So factoring is a cool trick here because it isolates it. If you can make it all equal to 0, if you have junk times junk equals 0, does it make sense you can consider those separately? If two numbers multiply to 0, then you can just look at them one at a time and say, well, then A is 0 is one of the answers. And I don't care what B is. B can be 27. But if A is 0, A times 27 or 0 times 27 is still 0. Or if B is 0, I don't care if A is 96. 96 times 0 is still 0. Well, that's what I'm going to do now. I can say, cool, I have kind of two cases. One is the sine of an angle equal to 0. And you should definitely be able to answer that in your head. Sine, you have memorized as a y coordinate. So you either draw this unit circle or you think about it in your head, and you should say, hey, there's two places where there's a y value of 0, right there and right there. Now you can go inverse sine of 0 on your calculator and get this, but you shouldn't need to. So there's two answers right there. Theta could be 0, or the angle alpha could be 0, or it could also be pi, either one of those two. Now that was a lot of algebra. I find myself wanting to go back up here and throw in, say, pi and sort of see, does that really produce 0? Does that really work? Kind of make sure, if you will, because it wouldn't be hard to screw that up. But then there's a second answer. When is 12 times the cosine of alpha minus 8 equal to 0? Well, notice there's only one trig expression, and it's not hard to get by itself. I can add 8 to both sides and divide by 12. And so the cosine of that angle is 8/12, or I guess that would be 2/3. Now that's a weird number. That's not a nice number like 0 or 1 or someplace that I can identify. I don't really know where that is. So I'm going to have to get my calculator out this time and take the inverse cosine of 2/3 to figure out what this angle is. And the problem would tell me whether I'm in radians or degrees. Probably it's in radians. So if I get my calculator in radians and say second cosine of 2/3, I get 0.841. But again, I'm interested. Can you kind of go, oh yeah, that makes sense. I just pushed calculator buttons and a number popped out, but I mean, a rabbit could have popped out of my calculator when I'm drawing a rabbit. Like I have no idea, but let's just stop and think for a second. So the angle, that's an angle, is 0.841. And so if you make it to here, does it make sense you're at 1.57? So that means I must have stopped, sure, it must be like right there. And then for the first time, I think, oh yeah, that actually makes sense. Because the cosine is the x coordinate, and doesn't that look like about 2/3 over? 1/3, 2/3. Hey, that looks about right. Okay, I got it now. That makes sense. But there's also a second answer to that. Since cosine of an angle is 2/3 and that's an x coordinate, isn't there another one down here? Doesn't that also have the same exact x coordinate of 2/3, positive 2/3? since this was up 0.841, then isn't that down 0.841? So I could say the other angle is negative 0.841. If nobody makes me write it otherwise, I'm done. Now the problem could say list the answers between, as they often do, 0 to 2 pi. In other words, it's saying, sorry, you can't write it that way. Well, that's easy to fix. If I went starting here, if I went all the way around the circle, got back to here again, that'd be 2 pi, and then back up 0.841. So 2 pi minus 0.841. Fine, I can do that. 2 pi minus that answer is 5.44. So fine, 5.44. Same answer. It's just another way to say it. Remember early in this class, that was called a coterminal angle, which just means another place that terminates and another way to terminate in the same location. Does that help? Yeah, so it looks like question 3, 4, and 5 are all kind of that general style. Talk to me. What do you say about that?
It makes a lot more sense when you explain it than when I watch the videos when I'm doing the homework.
And I would say it's normal learning. If I explain something and if I do a good job, and then you kind of say, you know, as you're sitting there listening and thinking, you kind of think to yourself, okay, that makes sense to me. And then you go off on your own, and then you're presented with a problem and you realize, uh-oh, that doesn't make as much sense as I thought it did now that I'm all by myself. And then you bang your head against a wall for, 30 minutes trying to work it out, maybe watch videos, try stuff and so forth. But I just want you to understand that's a super important part of the learning process. Because then if you have questions and I say something, the second time I say something about it, because we're talking one-on-one, then it's going to go in really deep. Like that's normal learning behavior. Me saying it once and then you got it, you're pretty sharp if that's you. That's not typical. So bug me about things like this. That's really important. I'd say it takes at least twice. And then
Definitely how I learn. If I don't hear it more than once, then I'm not going to remember it.
Yeah. Well, and where you want to get with this stuff is beyond memorization if possible. But you can see a question like this depends on a ton of things, like all the algebra that you learned about how to factor things. I could see it not occurring to you when you're sitting there staring at this step right here, thinking, okay, I wrote it that way, but that didn't do me any good. It's even worse. And so I feel like I got it wrong. The fact that you can factor it like I did here, that's depending on like a whole previous class. And, is that present in your mind right now? I mean, in some respects, this problem asks you to know everything you've ever learned about algebra. So that's a pretty big ask. So not weird to screw that up. Okay. Awesome. Let me see here. Just want to double check, make sure I know what we're talking about tonight, because I think it's chapter 8.1, which, if I remember right, we have a couple of all week to talk about non-right triangles and the law of sines and the law of cosines, which is just absolutely wonderful. And much more useful. I mentioned to you that those 2 nights of identities we did, and it's really unusual stuff. It comes up when the calculus class I was teaching yesterday or not yesterday, but Thursday was dying because of the lack of the knowledge that I'm teaching you right now and the ability to understand how sine and cosine is right triangles and so forth. We're using that knowledge that you're learning right here, right now in the calculus. So on your formula sheet, let me see, I'm sure it's on this formula sheet. Except for it isn't. There it is. So we're not going to belabor this point, but these two sheets are the formulas we're going to be looking at now. And of course, your first glance should be very daunting. Those look very intimidating. But let's make them ourselves. And what this has to do with is non-right triangles. So trig only applies to right triangles. Let me show you what I mean. Feeling the need to be drawing on graph paper. So I want to see if we can do this right now. Now, switch your calculator to degree mode right now, and knowing nothing more than SOHCAHTOA, I want to see if you can figure something out. So if I give you this triangle right here, and I don't know, let's say this side is 12. I won't call it 12 feet or 12 inches or 12 centimeters. I'll just call it 12. And let's say this side over here, let's say I drew it longer. So let's call that, I don't know, 16. And this angle right here looks less than 90, but more than 45. So I don't know, I'll call it 68 degrees. Do you agree that if I drew a line that was 12 inches long and then I turned 68 degrees and then I drew a line that was 16 inches long, would you agree that if I wanted a triangle, I have no choices? I have no choice but to come back and just connect these two sides over here. And so my question is ultimately, could you calculate the length of that side? Like if it's automatic, if that side is automatically determined by the 12, the 68, and the 16, then could you calculate the length of that side? Now you should say trig doesn't work in this triangle. It's very important you understand that. No trig. Because trig works where? Right triangles only. However, can't you make right triangles out of that triangle? So that's what I want you to do. If I drop this line down right here, creating now two right triangles, boom, trig is back in play. So work your way over there, knowing nothing more than SOHCAHTOA. So it is really true that there's no such thing as trig. The word trigonometry, trig is the TRI is triangle, and nometry is measurement. This whole class is triangle measurement. But any triangle, even a non-right triangle, can be broken into right triangles, and so then trig applies. And it turns out any shape you draw, even like a rectangle, can be broken into two right triangles. A pentagon could be broken into right triangles. So any shape that has straight sides, you can actually figure everything out about it just based on trig. Did you start like this? Do you agree that you don't know enough about this triangle over here? Do you understand that that 16 is broken into two pieces, but they're not cut in half? And I don't know how much. In other words, is this one 2 and this one 14? Or is this one 4 and this one 12? Or are they even decimals? You don't know that yet. So you actually don't know anything about the triangle on the right, but you know two things about the one on the left. So you should have started there. So I'll temporarily call this length A. So the 68-degree angle, A would be the opposite, 12 would be the hypotenuse. Oh, opposite and hypotenuse, that's a sine problem. Sine of an angle equals opposite over hypotenuse. Cool. That means A would be equal to 12 times the sine of 68 degrees. Is this easy? I hope this is easy. If you studied earlier and made sense of it between your teacher doing a good job and you studying, hopefully that's not new to you. So I got A is approximately 11.126. So I'm gonna note that. Now notice I never asked for that. I didn't want to know that. I want to know this. But I don't let's give it some time. Let's work our way over there. And in the same logic, could you not find this length over here, which I guess I'll call B, that length? Wouldn't that be cosine of an angle is adjacent over hypotenuse? And so I could multiply both sides by 12. And in a similar way, I could know what B is. And I got 4.495. You're getting decimals that go on forever, so you're sort of having to round them off. Again, in a sense, all worthless because that is not what I asked for. However, do you notice that A is a part of that second right triangle? And now that you know B is 4.495, since you know this entire length here is 16, then isn't this length 16 minus 4.495? Which makes this length 11.505. So do you see how you're making inroads on the other triangle? Because the hypotenuse of this other triangle is what you'd like to know, but you didn't know anything about it. Well, now don't you know two things about it? So what are you going to do with these two things? 11.126. What can you do with these two numbers to give you that one?
Pythagorean theorem.
Yeah. You're more than welcome to go figure out other angles or anything else you want, but can't you just use the Pythagorean theorem on those? And by the way, since those are so close to each other, would you agree that means these two angles right here are almost 45 degrees without even punching any buttons? Those two lengths are pretty close to the same. Not that you even need to calculate them.
Perhaps I didn't do that.
And also, since this angle is across from 11.05 and that's a hair bigger, if I had to guess, I'm going to erase this, but I'd say this one is just a hair bigger than 45, like 45.5. And maybe this one's 44.5 or something like that. Like they're darn close to each other. Across from 11.126 must be a slightly smaller angle, right? It's very important to understand this. Between my hands, if I have a tiny angle, then between my fingertips, doesn't that make that a tiny side? If I have a huge angle, then isn't the distance between my fingertips a huge side? Big angles have big sides. Small angles have small sides. That's just cool to point out. We're going to need that in this section if you're going to have any conceptual understanding. So I'm home free. All I have to do is Pythagorean theorem. To get this other side, I just have to take 11.126 and square it, 11.505 and square it, add those together in square root. And so my unknown side is approximately 11.126 squared plus 505 squared. Bam. Square root 16. It's darn close to 16. 16.005. So that's kind of interesting. It was almost the same size as this side over here, which is just kind of dumb luck. So I was able to figure out stuff in that triangle, even though it was a non-right triangle. Do you agree with that? You understand that logic? So would you also agree that all the stuff I built for this, like this number and this number, I never really needed those. Now I needed them to get where I was going, but I did not ultimately need them. In the end, I just did all that work for this number, and now I'm just going to throw all the other stuff in the trash. Does that make sense? So what mathematicians do is they say, wow, that took a lot of time to work our way over there. And so is there anything I could do that would like speed that up? Because I never really needed to know those other two lengths. They were not part. 11.126 and 11.505 were not really part of the original triangle. Like all I was really ever concerned about is this original triangle. And so is there some way I could kind of work my way over there a little bit faster? All right. Let's go back and do what algebra is good for. Now, would you agree that was a lot of work for one question? And now if I went back and I changed the 12, the 16, and the 68 to something else, would you agree you got to start all over and do it again? What mathematicians do is say, is there some way that I could do this one time and never have to do it again? And that's the law of sines and the law of cosines. Slow me down, interrupt immediately. Let's try this again. Except, oh boy, let's see. I'm going to call this theta. I'm going to call this side X and this side Y. And so those were known to us. So what I want to do is see, can I do with X, Y, and theta the same thing and create a formula to get what I'll call Z over there. So we're treating X, theta, and Y the same way we just treated these other numbers. And so let's see if we can do this. Again, interrupt. I'd like you to track with this. So if I'm going too fast, I want you to stop me. Did we not agree a second ago that that A length was 12 times the sine of 68? So if I redid this problem, wouldn't it be x times the sine of theta? Isn't that how tall that would be? And this length down here was B, and that was 12 times the cosine of 68. So wouldn't that be x times the cosine of the angle? And then to get this length, didn't we go, I don't think I wrote that down. Yeah, I did. I wrote it down right here. Didn't we take this overall length 16 over here? Since that was how far the whole thing was, and then we subtracted from it. So if this entire length is y, then isn't this blue length y minus x times the cosine of theta? And then what?
I lost you when you started talking about cosines. Why did you use? Because I didn't use cosine to get the answer. I did it, I guess, a backwards way.
That's okay. There's lots of ways you can do this. I'm just going to continue with what I did, but let me give you a second just to soak on this. So we said to find A right here, we said, hey, the sine of 68 would be A over 12. And then to solve for A, since it's divided by 12, I'll multiply by 12. So A is 12 times the sine of 68. That's what that length is. Well, for us, that would be not 12, but x. And the sine of what angle? Well, theta. So this 12 sine of 68 is this vertical length here. Well, then x times the sine of theta would be this vertical length. And similarly, this length was 12 times the cosine of 68. So for us, that would be x times the cosine of theta. And once we found out that distance was 4.495, we said, cool, then that means this distance would be 16 minus 4.95, and that'd be this length. So this would be not 16, but y minus that length right there, which is x cosine of theta. So I have those two lengths. And so then to finish this, didn't I say then that z, and I'm just rewriting what we said right here, z would be equal to those two numbers, 11.126 and 11.505, squared and added together and square rooted. It's just for us, that's x times the cosine of theta squared plus this second length here, y minus x cosine of theta squared and square
Do
rooted.
you mean x sine theta squared for the thing written in red?
Yes, I do.
Okay.
You got excited. Thank you for catching that. Right, x times the sine of theta. Now, just for the fun of it, type that in your calculator. Except put the numbers in we just put into it. So just to see that it works, like for us, the second ago for us, x was 12 and theta was 68 and y was 16, x was 12, theta was 68. Can you type that whole expression in your calculator and have it spit out that 16.05? Notice you're never even writing down all the other numbers. So square root, you'd have to have a giant parenthesis, x times the sine, oops. I want to put the numbers in it. 12 sine of 68, close the parentheses, square it. And I think sine makes you put a parenthesis, so you'll end up with a double parenthesis there. Plus 16 minus 12 cosine of 68, close this parenthesis, square it, and then close the one that started the square root. If I hit enter, I should get about 16.005, except it'll actually be more accurate because remember I rounded a whole bunch before? I rounded all the steps along the way. Now by itself, that just looks like, that's just really a complicated looking formula. But does it make sense that saved you a bunch of time? Like if you got in this mess again, that'd be kind of cool just to be able to plug two different sides and one angle into that and just have it spit out the answer. Here's where it gets cool. Let's see if we can clean that mess up a little bit. Well, first of all, I could just square both sides to get rid of that square root. And if I'm squaring x times the sine of theta, doesn't that mean there's an x squared and a sine squared? Do you agree with that? But why is that more complicated? Why is that a lot harder to square?
There's a subtraction in there.
Yeah. So this really means y minus x cosine of theta times y minus x cosine of theta. Again, you know algebra. Y times y. I like to ask students, what's y times y? And they'll say y squared, you know, and I kind of tease them like, you say that like you just did something. You just wrote it differently. Y squared means y times y. So you wrote it a little differently. Fine. And then y times x times the cosine of theta. Like math is so easy with letters because you can't actually, there's no such thing as math with letters. Y times x times cosine of theta is y times x times the cosine of theta. You can't actually do it. You're just writing that you're going to do it. And then interestingly, though, when you multiply this out, you get another one. You get another x times y times the cosine of theta. And then lastly, negative x times negative x is x positive x squared. And cosine of theta times cosine of theta is cosine of theta squared. Fine. So let's write that out. So plus, I've got a y squared. I've got now two of these. Notice you have one of them minus another one. If you have minus 3 times minus 3, that's minus 6. You double it. That's what I have here. I have minus one of them minus another one of them. Isn't that minus 2 of them? And then plus x squared cosine squared theta. Now again, your gut reaction to this should be, this is going nowhere. Like this is a gigantic disaster. This is, I'd rather just do this with soap.
I like just the pre-cleanup version better.
Yeah, like doesn't it look better here? And then also there should be part of you that says, you know, la 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 la, I'm not listening because all you had to know is SOHCAHTOA to get this answer. You're not wrong. Draw right triangles, and then so it takes a few more steps. This formula looks terrifying. However, it's about to actually take kind of a really cool turn. Watch this. Notice these two things right here. Notice you have 4 terms there because there's a plus sign here and a minus sign here and a plus sign there. There's 4 different terms. Does it make sense because both of these terms have an x squared? You could actually take that x squared out, which is nothing more than the distributive law. Perhaps you can see why I just did that. And then there's other junk. I just am rewriting it because I can't do anything with that. But what's really cool about this statement right here? This is what the identities are actually for. They show up occasionally to save you a bunch of time. What is sine squared of an angle plus the cosine squared of an angle?
1.
1. Which means, and this, my friends, is called the law of cosines. If it wasn't for that simplification, I would agree that this was an utter waste of time. But I'd like you to look at something kind of neat. So this actually leaves z squared equals x squared plus y squared. I'm going to stop there for just a second. What does that look like?
Looks like Pythagorean theorem.
Doesn't it look like
Pythagorean
Pythagorean
theorem.
theorem? Except for the Pythagorean theorem doesn't work in non-right triangles. This wasn't a right triangle.
I just said it looks like that. I
Yeah. No,
don't know what else it could be.
no, that's what I wanted you to say. It looks like the Pythagorean theorem. And so basically the Pythagorean theorem works in non-right triangles. It's just, you got to throw this little thing in there as well. Now that actually will save you a little bit of time because it just got small enough that all of a sudden I'm thinking this might be useful now. So again, I find myself wanting to go, really, that works? Again, you try this. A second ago, we said X was 12 and Y was 16, did we not? Type that whole mess into your calculator. Take the time to do this. Type that whole mess into your calculator and then hit square root. You're going to get the same answer we just got a minute ago, except this just literally took you 5 seconds. Whereas the original method, when we broke it into right triangles, took 5 minutes.
I am impressed. Your number wizardry never ceases to amaze me.
Nerds loose in society. Now, you probably, I'll elaborate on this in a minute, but you probably won't believe this, but I use this in my life today. I'll show you a picture of it. I don't think I'm going to take the time to get it to look good. I'm just going to show you a picture of it. I made something today. Where is it? Is this going to work? What is that? I know you don't know what it is, but what
It's a
shape?
hexagon.
So turns out my daughter's getting married in a week and a half, and she wanted a hexagon. I don't know, what do you call it? You stand in front of it to get married. What do you call that thing?
Altar?
Kind of an altar. Kind of like a, I don't know, people stand in front of gazebos and walk. You want to stand in front of something cool, right? You know, a tree or bushes or something. Anyway, she saw that on Pinterest, and so it's like, Dad, can you make that? But I had to use trigonometry to make it. And there's no triangles there. I had to put them there. I had to make them. And I could not build it if I did not do that. You understand that? I got out a chop saw and I cut the board at a certain angle. I had to calculate what that angle was. If I didn't know the angle, then I don't get to build the shape. I mean, that's what math is in the real world. It's like, if you're the person that can actually do this stuff, then you can make stuff other people can't make. And that's kind of cool, right? I use this all the time in construction. So now let me be a little more formal about this. This is the way the law of cosines is usually written out, just so that you can help keep it straight. If you're given a non-right triangle, and we'll call these sides A, B, and C, and we'll call the angle across from A capital A, and the angle across from B capital B, and the angle across from C capital C. Try to make that look like a lowercase c. You need to notice something really important about this. There were 3 sides in this triangle back here, Z, X, and Y. Did you notice theta was across from Z? That's extremely important. In other words, when you look at this formula that we just made, there were 3 sides, Z, 12, and 16. The one that was across from 68 is the one that's over there by itself. Does that make sense? You can't mix this up. So in other words, if I said, okay, fine, let's use this formula to find, I don't know, B. I want to find B. B squared. Well, it's the other 2 sides squared, A squared plus C squared, minus 2 times A times C, the same exact 2. But then the cosine of, well, what angle? Notice I've got 3 angles to choose from. Which angle?
B.
It's the one that is across from whichever one you chose to put by itself. So it's a neat formula, but it comes at a cost. Like, you got to think about what order to put all this stuff in. B. Oops, that was the wrong thing to do. Some books will even write them all out. I don't even know if this is what happened on yours, but again, solve it for something else. Fine, let's put C over there by itself. Okay, well then the other 2 letters will be added together and squared. It'll always be minus those 2 multiplied together, but now the cosine of the angle across from C. What's across from C? C. See what I mean? Now I want you to notice something. A second ago, we had 12, 16, and 68 degrees. Would you agree that what we knew here was a side and then an angle and then a side? Like, that's where this works, is when you know a side, an angle, and a side. You got to know 2 sides and 1 angle for this formula to work. Does that make sense? And not only that, the angle has to be between the 2 sides. Side angle is not the same thing. The angle's got to be between those 2 sides or this doesn't work. So it's a wonderful shortcut, but it kind of comes at a cost. Now quickly, just to make sure you got this, let me just make up a problem. This angle is 50 degrees. This side is 8 and this side is 7. And I would like you to find X over there. Can you set up the law of cosines, skip all the right triangles in the middle, save yourself a little bit of time, and tell me what angle X is? And if you have that note sheet printed out, like be looking at that because you're going to have that note sheet for the test. But maybe you don't need it right now while it's just kind of fresh in your mind. Stuff I showed you the last couple of days is kind of neat. It works good for advanced math classes, but you can actually make money. You can actually build stuff with this one. Like this one's cool. I mean, to not know this is kind of a bummer. This is actually useful. And I think I told you my favorite part of math is when you can actually do stuff with it, when you can actually build things or actually use it, not just pretend to use it. I'm going to show you something cool. So I think I also mentioned to you guys, I draw house plans on the side. That's kind of my side job. Maybe I didn't say that. But I use this program called AutoCAD, and it's a $3,000 pencil. But watch the things it can do. So I'm typing the command down here, L for line, and I'm going to draw a line that is 7 long. So I hit 7. So there's a line that's 7. And let's see, how am I going to do this? Actually, I think I'll do this a little easier. I'm going to draw the line straight across 7. Now, this is really cool for you guys to see because it turns out you got to know trigonometry to use AutoCAD. So do you see over here in the corner how it says there's an XY axis? So what I just did is I took off from here and I went right 7. Now what I'd like to do is make this angle right here a 50-degree angle. Well, AutoCAD, do you see my cursor over there? Do you see how it calls that 0 degrees? You guys know that because you took this class. That's 0 degrees. So it actually is labeled just the way you learned it in the real world. So this angle up here is 90. Do you see how it says 90 degrees? Over here, 180. Of course, it's not in radians, right? Like radians is not the language of practical stuff like building arbors and things like that. That's what it's called, an arbor. That's 270 degrees. And so I can get it to stick on 50 degrees by typing the less than sign. And if I say 50, you see how it just stuck on 50 degrees? And now it's waiting for me to say, how long would you like this? And I'm going to say 8. So would you agree I just drew with my $3,000 pencil a perfect triangle that matches what we just described? Now I'm just going to go over here and ask it, how long is that? Was that the answer you got?
I think I put it in wrong. Because
Yeah, that's what I got.
Me too.
So fix it if you didn't get that. But that's why this program costs $3,000, is because it has what I'm teaching you built into it. Did you notice I didn't have to know the law of cosines to get that? It has many such things like that in it as a part of this program. It calculates all kinds of things. It'll calculate areas. Watch this. If I draw a random triangle over here, and then I come back and I say, I would really like to know what size that angle is right there. It says, there you go, it's 34 degrees. Like I didn't have to do, it's not a right triangle, but all I do is just ask it stuff and it tells me. That's because the law of sines and the law of cosines are built into it. So in your world, most people will say, I don't need that. Well, that's because somebody made a program that cost a bunch of money, or maybe a cheap app on your phone that's like $9 or something that does that automatically. That's kind of cool. So quickly, just to make sure you didn't suck this up, because we're going to build on this idea and, do all kinds of things with this. So let's just make sure. How did you know which of the three sides, X, 7, and 8, goes by itself? Because the only angle you know is 50. So the one across from that's got to be the one by itself. So you'd say X squared equals, what do I put next? Is it 7 or is it 8? Is it 7 squared plus 8 squared, or 8 squared plus 7 squared?
I did 7 squared plus 8 squared, but I don't really think it matters, does it?
No, because when you add numbers, 3 plus 5 is the same as 5 plus 3. So you don't care. Right?
All right, cool. I
And
thought that was a trick question. I was like, is it supposed to be 8 squared plus 7 squared? Anyways,
so yeah,
and I did -2 times 7 times 8.
the same thing is true here because you're multiplying them. Isn't 8 times 7 the same as 7 times 8? So I don't care what order I write those in. I don't even have to pay attention. But the important thing is I'm taking the cosine of the angle across from the one that I put by myself. And I really like this formula because notice everything on the other side is numbers. So I can just say, calculator, tell me what that is, and I'll take the square root of it, right? Easy. Type that whole mess in. So, okay, that's pretty sweet. That's not so hard. I hope you agree. So X is, just to have it in the notes, approximately 6.404. Now that we know this side is approximately 6.404, would you say there's any way I could calculate this angle over here if I wanted to know it? I'm going to call that angle A. Do we know enough to do that?
Yes. Because now we have the side angle side. Oh, wait, never mind. Maybe we don't.
I'm giving you some think time, and I purposely asked the question in such a way as not to make it obvious if the answer is yes or no by my tone of voice. Let's solve a similar problem. What if I said these sides are 7, 8, 9? Actually, that's too close to the previous problem. Let's make it 5, 7, 4. Is there a way to find? So what if I know 3 sides? I just did that in AutoCAD a second ago, didn't I? I drew 3 sides and I said, hey, what's that angle over there? Does law of cosines apply here? By the way, do you see why it's called law of cosines? It's got a cosine in it.
I would assume you can take the inverse cosine to get the angle.
I mean, didn't this formula back here have 4 unknowns? Little b, little a, little c, and an angle. And if you know 3 of them, shouldn't you be able to find the 4th? The answer is yeah, the law of cosines applies there. Which one do I put by itself? The 4 or the 5 or the 7?
The 5.
5. 5 squared equals, I don't care which is which, 4 squared plus 7, 7 squared plus 4, minus 2 times 4 times 7 times the cosine of the angle across from the 5. Now, I'm not as happy with this equation because the thing I want to know is not already solved, right? Back here, I really like this equation because the thing I was trying to solve for, x, was already by itself. But I'm going to give you a second to think about that. You should be able to solve for cosine. That's why you practice those boring equation solving problems earlier. Here's like a place where it's actually kind of cool. So can you solve for cosine? Notice, unlike that ridiculous question we started the class with, there's not like a whole bunch of cosines and sines. That's not cosine of 2a, none of that nonsense. It's just cosine. So get rid of the 4s and the 7s and the 2s and all that stuff. Do you understand what order to get rid of that stuff in?
And
Let me give you a second to either get this right or get this wrong. This is what I used for that arbor today, by the way, because I knew the side lengths, but I just didn't know what angles to cut. I needed to know what angles so I could move the chop saw and cut them.
I got 44.415.
Anybody agree or disagree with
Me
Logan?
too.
Angel got the same thing?
Yeah, I just got there as well.
Okay, so that's a good sign, right? 3 of you got that? Let me catch up to you. So if there's math to do, do it. Like 25, 5 squared is 25. You should certainly do that. And 4 squared is 16. And 7 squared is 49. And 2 times 4 times 7, that's 8 times 7, that's 56. And then I can add these together, and that's 65. And then 65 minus 56 is 9. Except for I can't do what I just did. Do you understand that? Some of you did that. That's a common dumb mistake. And I don't mean like you're dumb, but just an algebra goof. Why can't you do that?
As the 56 is attached to the cosine, it's being multiplied.
Yeah, order of operations. Can you subtract before you've multiplied in the order of operations? No. You got to have reasons. If somebody says, no, don't do that, then that becomes rule number 900, and you'll never keep them all straight. Order of operations. So I can't subtract before I've multiplied. And so you're right, Cole. The fact that it's attached to the cosine means you can't do that. But it's a common mistake people make here. Also, notice if you did do that, you run into a problem here. Can the cosine of an angle be 25 over 9? Cosine is adjacent over hypotenuse. So could you have angle A where the adjacent is 25 and the hypotenuse is 9? Something wrong here. See what I'm saying? Go away. So what you should be doing is subtracting 65 from both sides. So that's negative 40. Now you can divide by negative 56. And we very much want the other side of that to be less than 1 on the unit circle, right? The cosine of an angle has to be less than 1 because sines and cosines are x's and y's on the unit circle. They got to be less than 1. So now if you just take the inverse cosine of 40 over 56, then you will get angle A. That's how you get rid of cosine, inverse cosine. Notice the negatives go away. Second cosine of 40 divided by 56 in parentheses. Yeah, I agree with you. So A is approximately, round it however the heck you want, 44.4 degrees. We'll call it that, close enough. So couldn't I repeat this and find all the angles in that triangle if I wanted to? Again, just because it's kind of cool to notice, and also because I'd like to teach you to think instead of just get boring math problems correct. Let's go draw this in AutoCAD. So here's a thought question for you. If I'm drawing something and somebody wants something 7 feet long, and now they want this side to be 4 and this side to be 5, what's wrong with what I'm doing right here? If I say, okay, I'm going to make that side, let's see, 5. So I'm aiming right there and I say 5. What's wrong with that? Does it make that side's not 4? How am I going to draw that correctly? Does it make sense? I can't just draw that 5 any place I want. I got to draw it at the right angle. And apparently I drew this angle way too big because that other side was too long. Here's a cool trick. If I go in here and draw a circle over here of length 5, and I go over here and I draw a circle of length 4, then there's where I need to draw I'm using math skills all the time. Uh-oh. Let's make sure I didn't screw this up. Let's make sure that these are all the size they're supposed to be. It's looking good so far. Cool. And we found the angle across from 5, right? So notice it's rounded to a whole number. I can control that in AutoCAD. I can get it to tell me to 1 decimal place or 2 decimal places. 44.4 rounds to 44. So notice I don't have to do this. I can draw things in AutoCAD and I can cheat and get the answers to these kinds of problems. So that's kind of cool. Since I'm here, what the heck is that? Uh-oh.
Too much running at once.
Yeah, I think I freaked it out.
It was too much math.
Too much math. So that's what I was building. It's basically 4 feet long. So it's like 6 feet, 8 inches tall. And so I was able to draw this in AutoCAD. And the main angle I needed is this angle right here. Because that's the piece I had to cut. And that angle is 60 degrees. So that's what I cut, a whole bunch of 60-degree angles to make that shape. Okay. So that's pretty powerful. I can figure out anything I want. Now, because I don't want to take the time to have you find the other ones, I just want to show you one thing really quick. If you did go back and calculate the other angles, I'll tell you what those are. This angle over here is 101.5 degrees. This angle over here is 34 degrees. And let me write in the one that we just got, which is about 44.5 degrees. What do you notice about the sides and the angles in this? Like, let's say you did go back and find the other two angles. And so great, you're all done. Now you know everything about the triangle. You know all its angles. What do you notice about the angle across from 4? I know I'm asking you to read my.
It has the smallest angle.
Yeah, that's what I was saying before. If 4 is the smallest side for my fingertips, then isn't the angle across from it going to be the smallest angle? And the medium-sized side, 5 is across from the medium-sized angle, and the big side's across from the big angle. Notice 4 and 5 are pretty close to each other. So 44 and 34 are pretty close to each other, but 7's way bigger. The angle across from it's way bigger. Like, use that to check your work sometimes. If the biggest side is not across from the biggest angle, you got it wrong. Something's wrong. And you can see with all the algebra we got to do here that you could screw up the algebra genuinely because like you don't know your stuff, or you could just actually poke a button wrong. Like you entered 65 in your calculator, but the 6 didn't show up. You hit 65, but only the 5 went in. Could even be not a mistake on your part, but just kind of an accident on the calculator. But check it, make sure it makes sense. If it's a high stakes kind of a question, like a test, even if you weren't asked to find all the angles, I might go ahead and find them all just to make sure I didn't screw up. Let's see. So I'm going to make up a problem that law of cosines won't work for. Let me think about this here for a second. Let's see. What if I told you that this side was 15 and these two angles look about the same, but I'll just make them slightly different. Say this one's 58 degrees and this one's a little smaller, 56 degrees. Would you agree law of cosines won't work there? Why won't it work?
Because it's not side angle side. It's not SAS.
Well,
Has no sass.
notice this one was side, side, side. So it worked for side, 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 and it worked for side, angle, side. This one, though, is angle, side, angle. Why won't it work? Or does it work? Well, remember the law of cosines had 3 sides in it. Does it make sense we only have 1? That's going to be a problem. Now, can you write it? Could you write out the law of sines or the law of cosines? Yes, you could. But you're going to have too many unknowns in it. Do you see what I'm saying? So as an example, well, first of all, would you agree that you could actually calculate that angle without having to know much? What are the angles in a triangle add up to?
180.
180.
180. So if you know 2 angles, you always know 3. So that means if I'll just call this angle A. So I could say angle A is 66 degrees because now they all add up to 180. So that's cool. And if I call this length over here, since I don't know what it is, I'll call this X and this Y. Like, you're more than welcome to use the law of cosines. So for instance, you could say 15 squared equals, notice I just randomly picked that, equals x squared plus y squared minus 2xy cosine of what angle?
A or 66.
The one across from 15. 15 is by itself. This is true, but not helpful. Why is it not helpful?
There's
Too
too
many
many
variables.
unknowns.
Too many unknowns. You see the problem? Great, it's true. It's not like it's not true. It just isn't helpful. So the problem is with law of cosines, you got to know 2 sides or you're not going to be able to do it. If 2 sides are missing, all 3 sides are in the formula. Does that make sense? They're all in the formula. So if you only know 1 side, it's not going to work. So does that mean we're hosed? Can't do it.
Would you not be able to write it with like X being by itself?
We'd still have right or y on the right side, so we'd still have both x and y in the equation.
Yeah, that's right. Let's take just a second to do that. So if you put x by itself, that equals 15 squared plus y squared minus 2 times y times 15 times the cosine of what angle?
58.
X is by itself, 58. Still not helpful because there's still an x and a y. They're in different locations, but they're still there. So also true, but not helpful. Now, what I'd like you to do is say, well, who cares? I have SOHCAHTOA, I can make right triangles out of it. So let's do that. Go slow. Copy. Paste. So let's see. I'm just going to fill in the 66 instead of making it a variable. And again, it's important to understand this one is angle side angle. So law of cosines is out. But can you still do it? Well, I want to say, yeah. And let's say that our goal was to find this side over here. I'll call that one, well, I called it y earlier, so let's just call it y again. Let's say your goal was to find y over there. Well, couldn't you do the same thing we did at the start? Let's see, I'm going to bust this thing into 2 right triangles. Now, would you agree I just screwed up my 58-degree angle? Did I cut it in half? No, not for sure. And notice I tried to draw this at 90 degrees down here, but you did not cut 58 in half. So you totally screwed that angle up there. But again, I want to give you a second. Now, would you agree that in this first right triangle over here, you know a side, you know an angle, and it's a right triangle. So can't you find everything out about that right triangle you want just using SOHCAHTOA? Well, then do it. And if you find everything out about that, then wouldn't you be able to work your way over and figure out what y is? See if you can do it.
Just as a question, to figure out what y is, would you be able to cut the triangle anywhere
Yeah,
into two right triangles?
that's right. In other words, you could cut these
Okay.
different ways. Well, I wouldn't want to do this one. I'll erase this, but you wouldn't want to do this one. Why not? Why wouldn't you want to do it that way?
Because you don't have the side that you need. You'll lose
You're
the
splitting
15.
the side.
You just lost your 15. Does that make sense? And you didn't cut it in half. So you can cut it up any way you want to, but you just screwed up 15. So that one won't work. Wonderful question. It's very good practice just for regular trig. I'm going to catch up to you at least a little of the way. So I'm going to call that length A because I don't know what it is. And so wouldn't you be able to say that since the only angle I have is 56, the sine of 56 is opposite over hypotenuse. Notice 15 is the hypotenuse of that first triangle. I'm sort of working on the first triangle over here. So that means A is 15 times the sine of 56 degrees, which is 12.436 approximately. So that's really cool.
I got 13.612 for y.
Anybody else get that?
Yeah,
Nodded.
I did.
I got 13.617. I don't know how we got.
Rounding.
It's probably rounding.
Yeah. Notice that A, how many places do you carry that out? And by the way, you got to have to be a little bit careful in my open math, because if they say they want the answers to one decimal place, does it make sense you can't round that 12 off to one decimal place? Because you're going to use it for the next calculation. And by the time you get to the next one, it might make it off by too much. So if the problem says round to one decimal place, you better work to at least 2 or 3 the whole time and then wait till round at the end. So I carried it out pretty far here. But again, I like to get in the habit of saying approximately equal. I'm telling myself and anybody else looking at my work, dude, I rounded that off. Do you notice you can actually jump into the second triangle right now? Like you can abandon the first triangle because you now know another side in the other triangle because A is shared by both triangles. So couldn't I jump into that second triangle now? And well, actually look at that. It's interesting. It's the sign again. The sign of 66 is opposite, which is A over Y. And I know A now, 12.436. And so notice to solve for Y, Y is on the bottom. You gotta be a little bit more careful here. So I'll go a little more slowly. If I get rid of the fraction by multiplying both sides by Y, oh, okay, then Y is actually 12.436 divided by the sine of 66. And by the way, that number is still sitting in my calculator. Did you notice that? Why erase it and then write the wrong one? Why not just leave it in there and then say divided by the sine of 66? Divided by the sine of 66. So my answer is still perfect. I got 13.612. So mine's actually accurate to 3 decimal places right now because actually A was in my calculator out to like 9 decimal places. So that's just kind of cool. Think about accuracy. Sometimes it matters, sometimes it doesn't. So that's kind of cool. We actually just jumped over there really quickly. That was actually less trouble than the law of cosines. Did you notice that? Now, there's other things you could have found, but you didn't need to, right? You might have found other things, but now in hindsight, it's like, oh, I didn't really need to. I wasted my time. Now, just for a second, let's kind of, I'm going to kind of rewrite this problem a little bit. Let's pretend for a second I gave you 15 and I gave you 56. Did you notice we never even used 58? We used the 58 to get to the 66, so we needed that. But does it make sense in the end? This is the only numbers we really worked with. And then we made our way over here. Notice that's not angle, side, angle anymore. If you go in order, it's either angle, angle, side, or if you go the other way, side, angle, angle. But if I gave you the problem in the way that I just wrote this second one, do you notice actually how simple this answer actually was? Let's take a look back at what we just did a second ago. Didn't we say Y was equal to 12.436 divided by the sine of 66? But at one time, wasn't 12.436 actually 15 times the sine of 56? In the end, isn't that what we did to get Y as a shortcut? Now, it turns out this can be really easy to memorize, way easier than the law of cosines. Now, in my class, you don't need to memorize it. You got a sheet to look it up. But let's just mess with that just a little bit. If I took, let's see, if I took this angle and I divided it over to the other side, wouldn't I have that? Do you notice?
Why would you want to do that
Only
if
for
you could
numbers.
just plug that into your calculator?
Yeah, you wouldn't. But I'm saying in terms of memorizing what the law of sines is, do you notice that 15 is directly across from 66? And secondly, that y is directly across from 56? That's how you set these things up quickly and not have to memorize things. Now you're right. This statement already was solved for y and I'm done, right? And that's what you wanted. But remember, you got to set this up from scratch. And so back here, we had the law of cosines. Simply called because, well, it's got a cosine in it. But let's look at what we just saw a second ago. The law of sines, called because it just had a bunch of sines in it, didn't it? Basically says if you want to take any side you want, like B, and divide by the sine of the angle across from it, that'll be equal to any other side you want divided by the side across from it. You see how easy that is to memorize? That's why it's written that way. That's the law of sines. That's way easier to use. The law of cosines is a big ugly formula, squares and multiplications. It's a big mess. Law of sines is actually way simpler. This is the only two there are. If you have both of these, you can actually, as a shortcut, answer any missing parts in even non-right triangles. But it's very important you understand there's no such thing as trig except for right triangles. We made these from regular SOHCAHTOA, didn't we? Let's take a look at your formula sheet. Now, all of a sudden, we understand those. Notice they're using Greek letters. A over alpha, that's Greek letter for A. So A over the sine of alpha, that means those two have to be across from each other. Or B over the sine of beta, those have to be across from each other. Or C over, shoot, also I can't remember that one. Is it gamma? I forget which one that one is. It's embarrassing. Take my
It's gamma.
It's okay. It's not like you speak Greek or anything.
Yeah, I don't speak Greek. Notice it's also true if you want to flip them upside down. You can put the angle on top if you want, just be consistent. So they said, any triangle, and they use this phrase standard labeling. Well, that isn't very helpful. But again, they're just talking about, well, they picked sides of A, B, and C, and then they just chose Greek letters, A for alpha, B for beta, and then I think that's gamma. Like that's what they mean. Feel free to add that to your note sheet. I think it's better if you just use capital letters like capital A, capital B, capital C. so that it's a language that you understand. But it's common in advanced math. Anytime you see a Greek letter, it's actually a good thing. It helps you know, hey, that's an angle. Beautiful. Now, actually, I want you to try this. This is interesting. Turn your screens on if you can. I want to see your face. If you can't for some reason, fine. But unless you've lost your sight in one eye, you have what's called binocular vision. You have two eyes. Have you ever covered one of them up? Do this. And now, as far away as you can reach, I want you to try to grab something. Can you tell you don't have depth perception? If you try to grab something, you might grab too short. Just try to take your finger down and touch something on your screen and stop right where it is. I find myself grabbing and it's like, oh, I missed it. Whereas when you have two eyes, you're like, oh yeah, it's right there. And you can grab it really easy. You notice how you kind of suck at depth perception with only one eye? Have you ever played with that before? Why did I show you that? I'll show you.
Because that was trick. Your brain automatically does it.
Yeah, in a sense, your brain is doing what I just taught you. And that fact is the reason that we know so much about the solar system. So let's consider this. Here you are on Earth. You're a speck on Earth. And you look outside and you see a star. Dude, there's a star. How far away is that star? Would you agree that it could be really huge and really far away, or really close and really small and look the same to you? You've all probably always looked up at night and went, is that an airplane? How could you be so dumb as to mistake a star for an airplane? A star is like the sun. It's gigantic, and you thought it was an airplane. That's because it's so close, right? So it could be way out there and be gigantic, or it could be real close and be real small. Does that make sense? So how do we know how far that star is away? Because you see that, in books and so forth, they tell you, oh, that star is 900 light years away or whatever. It's because of binocular vision. It's because when you're on the Earth, flying around, well, this is the sun. And we fly around the sun. So here we are at one time over here, and we see this star over here, and then we fly around 6 months later, and now we're over here, and we see it yet again. Does it make sense that this is an angle side angle problem? In other words, that length right there, perhaps we are 93 million miles away from the sun. So the distance between your two eyeballs, if you will, in this scenario is 186 million miles away. And you are seeing that star from two different locations. Just like with two eyes, you can identify how far something is away from you. If you look at a star from two different locations as you fly around the Earth, you can know how far away it is. So you measure the angle between the sun and the star. Let's say that was 80 degrees. And then you go 6 months later, now you're over here. Let's say that angle was 84 degrees. You now know an angle, a side, and an angle. Does it make sense? You can find these two missing sides over here and kind of know how far that is away without ever leaving Earth. I mean, isn't that amazing? It's really cool. They have other more complicated ways called red shift and blue shift and so forth. But that's an example of why I had you kind of play around with your eyes. You're actually able to see things from two different locations. And so you can actually know where it is. Unbelievable that people figured this out before calculators and so forth. But notice that's an angle side angle problem. So I want you to do that. If this is, I'll just call it 186 instead of 186 million. And I would like you I'd just like you to figure out this length over here, X. This is 84. This is 80. Can you use the law of sines? The law of sines. Why would you want to use the law of sines? You don't have a choice. Law of cosines doesn't work. And more importantly, you don't want to use the law of cosines. It's bigger and uglier. Use law of sines if you can. But you got to know sides across from angles. Can you set up the law of sines and figure out how far that one side of that triangle is? Did you notice, I'm still going to give you some more time, but did you notice you had to figure out this angle over here for this to work? You know two angles, you always know the third. Because you got to know the angle across from 186, the only side you know, otherwise you can't set up the law of sines. Now you can set it up. Notice what I said earlier, 16 is the smallest angle. So 186 million miles is the small side. The other two are going to be bigger. Of course they are. The other stars, which are also suns, are way the heck out there. Notice it's almost like a proportion. Let me write this down. You could say X is to 80 degrees what 186 is to 16 degrees. That's like a proportion. Except for that's not true unless you add sine to it. Now it's true. But X has to be across from 80. And again, you could have done that upside down. I could have put the sines on top and the lengths on the bottom.
I got 664.6.
Let me see if I get the same thing. You should be able to write this out. In other words, multiply the sine of 80 to the other side. You should be able to do that algebraically without punching any buttons. So now I'm going to say 186 times the sine of 80 divided by the sine of 16. Yeah. X is 664.55. So that's 664 million miles away. By the way, in the case of stars, those angles are not 84 and 80. They're like 89.2. They're really close to 90 because the other stars are way the heck out there. When you look up at night, you can kind of tell. Remember, those are suns. They're the same as our sun, but they look teeny. They're way out there. So you don't get angles like this. Notice that's only like 4 times as far away as the sun is. Stars aren't that close. They're way further out there. And you can appreciate accuracy. You have to have some amazing tools to measure these accurately, because at this distance, being off by 1/10 of a degree would mean billions of miles. So I'm curious to know how that kind of stuff is done, especially by the ancient people who barely had telescopes and so forth. That's kind of cool, isn't it? In a practical sense. So before the glories of GPS, let me give you an example of a surveyor problem. So surveyors are the ones that mark property lines out. When you buy property, if you've never bought property, it's really expensive. So it's like, what did I just buy? Like, I want to make sure it's marked out exactly right. And where's my fence go and all that stuff. And so surveyors get paid to kind of make sure everything's in the right location. So what if you had a property line here and a property line here, but there was like a lake in between? And you said, how am I supposed to measure that? Because there's a lake in the way. I can't just lay a tape measure on the ground. So one of the things you could do, if you're a surveyor, is just go set up somewhere like over here. And you could measure this distance, 121 feet. And you could measure this distance, 193 feet. And you could measure this angle between it, 42 degrees. And does it make sense you could use what I showed you today? Let's see if we can do this really fast and then we'll get out of here. To find that distance right there, I'm gonna call that X. Notice that's kind of cool. Now again, this doesn't get used anymore by surveyors because they have GPS. They just walk over to this spot, take a shot, mark here, take a shot, and it just tells them the answer, which is cool, but also kind of a bummer in the sense that you're, learning all this math, and technology makes it so you don't have to do some of it, just like AutoCAD for me. But remember, all that survey equipment costs thousands of dollars, and so that's kind of the trade-off. So the question is that a law of sines or a law of cosines problem?
Cosines, side angle, side.
Yeah, it's cosines. Now you can memorize the angle, side angle, side, side stuff, but does it make sense for law of sines to work? You have to know a side across from an angle. You don't know that here. So you can write the law of sines down, but it isn't going to help you. You only know one angle, so that means you can't find any other angles easily. You know two sides, but they're not across from the angle, so you have to use law of cosines, which is kind of a bummer because it's the hard one. Anyway, see if you can get this. And once you get that, just for the fun of it, see if you can find this angle up here. And then we'll be done. Should be done right now because it's 7:20, but it's already late. Let's just keep going. Check your equation. For X, did you say, oh, I know 42 degrees? So the three sides, 121, 193, and x, the x is the one that's got to be by itself. Which remember, you're extremely glad for because that means it's already almost solved. And the cosine is the side, the angle across from the one you chose to put by itself, which is why it had to be by itself. Again, awesome. All I got to do is type that whole mess in. I don't have to do any algebra, just order of operations. And your calculator does that for you. So you just type that whole disaster in. And if you don't choke, you get 131. I'll say 0.1. In this case, you'd want to say feet because the problem was actual measurements. It's not 131, it's 131.1 feet. So law of cosines was necessary. Now, if you switch to A, now remember, you know all the sides now, which means a second ago we had all the sides and we used the law of cosines. But the law of cosines is a lot more trouble. Now, because we know 131, does it make sense you do know a side across from an angle now? So couldn't you say x, and I'll just put it in right now, save some time. You could say 131.1, maybe I should be carrying that out more decimal places, divided by the sine across from it is equal to 193 divided by the sine of the angle across from it, or upside down. In this case, it might have been better if I wrote it the other way. That's an easier formula, way easier than the law of cosines. I don't like fractions, so if I multiply the sine of A over to the other side and I multiply the sine of 42 over to the other side, now I don't have fractions anymore and I'm guaranteed not to get this wrong. Then I can divide by 131.1. Awesome. I have the sine of A by itself. I just have to figure out what that is as a number over there and then go inverse sine. Boom. I got it.
I got 80.086. And do we have to worry about the it being inverse giving us two possible angles with this?
We do. And that's why there's a tomorrow or Wednesday.
Lovely.
0.985 is what I got for that side. Remember when you go inverse sine, how there's two answers? Oh no. So I go second sine of 0.985 and I get what Nicholas said, 80.06, or A is 80.1 degrees. But unfortunately, that's actually wrong. It's the other one.
It's 99.914, if I'm thinking about it right.
So let's look at the unit circle. We're at 80 degrees, which is here. Oh yeah, that makes sense. The y coordinate sine of the angle is almost 1. Isn't that almost up to 1? So that looks about right. But wouldn't sine has another answer right over there, doesn't it? So unfortunately, A could be 80.1, or A could be, let's see, if that's 80.1 up to there, then isn't this, just reason it out, isn't that also 80.1? So I guess that'd be 180 minus 80.1, which is, yeah, 99.9. Which one? One of them's right, one of them's wrong. So Wednesday, we just need to talk about how to not get in that problem.
Well, wouldn't you do the like small angle with small side, big angle with big side?
Yeah, so let's just stare at that really quickly. So if it was 80.1, then this was 42, this was 131. I'm just rounding it off. This was 121 over here, and the angle, let's see, this is roughly 80 degrees up here. This side over here was 193. And if I take 180 minus 80 minus 42, I get 58 degrees over here. Is there anything wrong with that? Is the big side across from the big angle, small sides across from the small angle, medium sides across from the medium side?
No, the medium side is across from the little angle.
You notice it's not right?
So it's got to be the 99.9.
Yeah. So there really is two answers to inverse sine. Like, it kind of stinks to do inverse sine. And so if you drew this out, then it'd be like, oh yeah, I guess it's not that one, it's the 99. So you got to be a little careful with that. So I want to give you some advice about kind of how to handle that. Other than this weird situation. Now, anyway, we'll talk about it later. We're too late. I gotta shut up. But other than that, this isn't too hard. All right, get out of here or stay after and ask me questions.
Thank you.
Thank you.
Good night.
No, no.
Thank you.